Okay, in this video, we're going to continue our study of operations with events in probability. So you might be asked, and this is a review concept, to list the sample space of an experiment if there aren't too many possible outcomes. So for example, if there's a spinner with 1 through 3 on it and you're spinning it 3 times, you might be asked to list the entire sample space or all possible outcomes, and then maybe ask probability questions based on that. So you want to try to be systematic when listing out a sample space. For example, in this one, you could spin a 1 3 times in a row, and then you want to probably list out all the other options that start with a 1 on the first spin. Then you want to list out all the options that start with 2, and then all the options that start with 3, or you may come up with your own internal sort of organization system that makes sense for listing. In this case, that's going to be this entire sample space, which includes 27 things. And in order to double check if you've gotten them all, it can be helpful to use this little formula, which is that the number of possible outcomes in something like this is going to be the possible outcomes for just one trial. So basically, when you spin this spinner, there are 3 possibilities. Or when you flip a coin, there are 2 possibilities. Roll a dice, there are 6 possibilities. Whatever the total number of outcomes is for the one trial, raised to the power of however many trials you are doing it. So in this case, spinning it 3 times. So listing out can be the worst, and you should only do it if you're asked to. If it's a smaller number of outcomes, then you might just want to do a list. But if it's a large number of outcomes like this, there sometimes are easier ways for figuring out what your sample space is that you can then use to answer probability questions. For example, a sample space diagram. This is a way of showing all the possible outcomes of an event. It works well when there's only 2 trials being performed because you can organize a column and a row sort of array of your possibilities. So for example, here's a question that asks us to draw a sample space diagram for the scores when 2 dice are thrown. And so throwing 2 dice, you could organize a sample space diagram that looks something like this, where we've got across the top 1 through 6, down the side 1 through 6, and then every possible combination of rolls is written almost like a table, like a multiplication table. You could then actually calculate the sums if you wanted to. Notice it says for these probability questions, we're looking for the probabilities of obtaining a score of 6, so that would be the sum of the 2 rolls would equal 6, just based on the way this problem is written. Or a sample space diagram could even look like this. This is an even more efficient way of showing the possible results, where each dot represents one of the rolls, and you have to read across and up the table in order to figure out what each dot represents. But then you can answer questions. So like the probability of obtaining a 6, you'll notice that there's a little pattern. If you start highlighting the ones that total up to 6, you'll see they all occur in a diagonal row. So there's 5 out of 36 chance. Probability of throwing a double, so that's the 1, 1, 2, 2, 3, 3 option. Those also occur in a diagonal, so 6 out of 36. Probability of scoring less than 6, and those occur all above the diagonal that was the sum of 6. Below that, you'd have all the totals that were greater than 6. So it ends up being 10 out of 36. So a sample space diagram can be a nice systematic way of looking at your sample space and then calculating probabilities, which will appear as little patterns. So here's an experiment where a coin is tossed and a dice is rolled, and this also is a nice sample space diagram. Though truthfully, it's not that long of a list, so you could just do a list instead. And then we're asked to find the probability that in a single experiment, you get a head and a number less than 3 on the dice. So the sample space diagram looks like something like this, with each option shown, and then the probability that in a single experiment, you obtain a head and a number less than 3. I've highlighted those in yellow. That's the H1 and H2 options. So a 2 out of 12 or 1/6 probability. Here's a definition that you're going to need to know. So 2 events A and B are called independent if knowing that one of them occurs does not change the probability that the other one occurs. So we would say the events are independent, like tossing a coin and rolling a dice, because when you toss a coin, it's not going to affect the probabilities of your dice roll and vice versa. Something that wouldn't be independent would be like if you pull out the King of Hearts and then you don't put it back in, now you reach back into the deck of cards to pull out another one, your subsequent probabilities will have changed because there's only 51 cards remaining in the deck. So lots of things are independent that you can't use common sense to figure out. So instead we use a formula to determine if 2 events are independent in probability. And that formula is the simple multiplication rule for independent events. Let's pull up a screen shade here. So the multiplication rule for independent events says that if A and B are independent, then the probability of their intersection is equal to the probability of A times the probability of B. This is only true for independent events. So if I'm asked, hey, are A and B independent, I can check if this is true, and then I can determine, yes, if this is true, they are independent. No, if this is not true, then they're not independent. And sometimes there's surprising things that are actually not independent of each other. Like if I randomly selected a student from this school, the fact that they're a junior and the fact that they might be a male student are actually not independent events based on the breakdown of our student population. So you can't use common sense for independence. You have to check it using this formula. So here's an example of a Venn diagram where A, B, the intersection are labeled. The probability of A is actually 0.42 plus the 0.18, and the probability of B is the 0.18 plus the 0.12. So if I'm trying to see if these A and B are independent, it's not the same as mutually exclusive. It has to do with the relative sizes of these numbers. And so again, you can't know by looking at it. You must check with this formula. So are they independent? Here's the formula that we're going to use to check it. I put a little question mark over the equal sign because what I'm trying to determine is if the intersection probability, which is 0.18, is indeed equal to the product of A times B. So I have to set up this equation and see if it comes out equal on the left and right. If I simplify A and B, it comes out to 0.6 and 0.3. And when I multiply 0.6 times 0.3, I do get 0.018. So A and B in this picture are independent. But if any one of those numbers had been slightly different, the events wouldn't be independent. So you can't tell by looking at it. You have to evaluate the formula to check if two events are independent. So one bag contains 3 red and 2 white balls. Another bag contains 1 red and 4 white balls. And a ball is selected at random from each bag. So we have the story here enough to determine that if I select a ball from the first bag and then I select a ball from the second bag, the first result does not determine any changes in the probability of the second result. So these would be independent events happening. So I can use the independent events formula, which says that to multiply 2 probabilities together, you can get the intersection of both things happening. So like probability that both balls are red, I can do 3/5 from the first bag times 1/5 from the second bag to figure out the probability that both will be red. So that's 3 out of 25. Or the probability that the balls are different colors. So that's with a red from the first bag and a white from the second, or a white from the first and a red from the second. So that ends up being 2 possible pathways, if you imagine this like a tree diagram, that you are then adding together. So a total of 17 out of 25 chance that you'll get 2 balls that are a different color. And then the last one is at least 1 ball is white. So at least 1 is 1 minus the probability that none of them are white, right? Because there's a white-red, a red-white, or a white-white option. So the probability that at least 1 ball is white is the probability of 1 minus both balls being red. And since we had already calculated that, that ends up being the easiest way to determine the probability that at least 1 ball is white. Here's a simple example that seems more complicated than it is. The probability that you find a certain traffic light green on your way to work is 30%. So what's the probability that you would find it green on 2 consecutive days? So here again, we have the story enough to determine that finding the light green today is not going to impact whether I find it green tomorrow. So one day and the next day are independent events. And that means I can multiply them together to figure out the probability of both of them being green on 2 consecutive days. So I can do 0.3 times 0.3 and figure out that the probability is 0.09. And indeed, this would work for 3 days in a row, or 4 days in a row, or 5 days in a row. And that's what this slide shows. That to figure out if it's probability of it being green on 5 days in a row, I can multiply the probability 0.3 times itself 5 times because we're assuming that it's independent, that if the light is green today, it's not going to change the probability of it being green tomorrow when I come to the light. And that is all.